So I expect some more people joining over the next couple of minutes, but let me slowly start to introduce our speaker today. So welcome everyone. Thank you very much for joining our joint ECE Data Science and Health Distinguished Seminar. Before presenting our speaker today, let me briefly go over some logistics. If you have any questions, you can write them in the Q&A chat. And towards the end of the talk, we're going to select some of those to be answered by our speaker. During the talk, we also monitor the Q&A in case there's any pressing clarification question that makes sense to address in the middle of the talk. Otherwise, we're going to address most of the questions towards the end. And actually, Professor Akane-Sano will be in charge of moderating the questions during the talk and at the end. The talk will also be recorded and uploaded to our YouTube channel for future access. That being said, it is my pleasure to present today Professor Mihaela van der Schaar as our distinguished speaker. Professor van der Schaar is the John Humphrey Plummer Professor of Machine Learning, AI and Medicine at the University of Cambridge, a fellow at the Alan Turing Institute in London, and a Chancellor's Professor at UCLA. She has been an IEEE Fellow for over a decade now. She has received numerous awards, including the Owen Prize on Preventative Medicine from the University of Cambridge in 2018, an NSF Career Award, 3 IBM Faculty Awards, many paper awards, and many other recognitions. One that especially caught my eye was the recognition for being the most cited female AI researcher in the UK in 2018. So an amazing repertoire of awards. Mihaela's research focus is on machine learning, AI, and operations research for healthcare and medicine nowadays. In addition to leading the Van der Schaar Lab, Mihaela is founder and director of the Cambridge Center for AI in Medicine. At a personal level, I've always been very impressed by the breadth of topics and methodologies that Professor van der Schaar has worked on, and she has served as a role model for me as a young professor. So Mihaela, so we briefly mentioned this. So we met in ICAPS 2013 in Vancouver. That was actually my first conference as a young PhD student. So I remember that you stopped by my poster, we had a discussion, and then a follow-up email. And at that point, I was working on things that were not super core signal processing. So when I saw that you were working on very broad topics like link formation among self-instantiated agents, social norm design, reputation protocol design, but from a formal mathematical perspective, I was immediately hooked, and I became a great fan of your work. Now you're focusing on healthcare, but Mihaela maintains that distinctive research creativity that makes her work so cool. So we are very glad to have you here. It is a sincere pleasure. So thank you, Mihaela, for joining, and the floor is all yours.
Thank you very, very much, Santiago, for inviting me. Such a pleasure to be talking. And I wish that I was in person visiting, but and hopefully this will be the case soon. And I really want to say it's especially a pleasure since we know each other for a long time. And also, of course, Rich Baranyuk and I know each other for also even longer than we know each other. Santiago will not tell how long, since this is quite a number of years. So thank you very much. Today I'm going to talk about why I believe that medicine and healthcare represent exciting topics, and they represent also new frontiers for machine learning. I'd like to start by thanking our research teams, the PhD students and postdocs in my lab, and especially I'd like to thank Dr. Ahmed Allah and Ioana Bica, because I'm going to highlight a lot their research in the talk today. So, of course, we know by now that machine learning has accomplished wonders in numerous areas, inclusively in engineering. But a variety of the domains in which machine learning has made a big impact is on well-defined problems where the solution is relatively easy to verify for a human being. In healthcare, this is slightly different because the problems are not always well posed. One needs to think carefully about how to model these different problems, and the notion of a solution may not often be well defined, and the solutions are at times even hard to verify by a human. So an example comes from the era of COVID-19, where we may see patients deteriorating in different ways than prior to COVID. And different types of interventions may be effective for one class of patients, but not for others. So this represents an enormous challenge for machine learning and in general data science, but also enormous opportunities. So the goal of our lab is to develop new machine learning problem formalisms, model and techniques with our overall goal of revolutionizing healthcare. So the mission of our group is to turn medicine from an art, which currently it is, to a science. So William Osler, the father of modern medicine, often said that medicine is very much an art. And I would argue that unfortunately, despite the recent advances, medicine still remains an art. And the reason behind it is because it is hard. However, with quantitative tools from machine learning and other areas, hopefully we can turn this art to a science. The focus of our lab is on 6 main research thrusts: developing machine learning for delivering bespoke medicine, where we are going beyond just precision medicine, one step further, and I'm going to briefly talk about that next. Understanding the basis and trajectories of health and disease, empowering clinical professionals and patients with a variety of tools and decision support systems, informing and improving clinical pathways, enabling better utilization of resources and reducing costs, transforming population health and public health policy, and enabling new discoveries, both clinical as well as new therapeutics. So our group's research agenda falls in 4 different categories. First, we often need to build machine learning on the basis of data that is difficult to share with the general public and the machine learning community because it's sensitive, private, clinical data. So an important research topic for our lab is to create synthetic data sets with high fidelity and high privacy guarantees. And in such a way, the machine learning community can engage with the powerful analytics on the basis of such synthetic data sets. And then as soon as these analytics have been developed, they can be brought in to the real data and they can work with high fidelity. So an important topic of our lab is to develop synthetic data sets. In terms of analytics, we are working on many different areas, inclusively individualized treatment effects, time series analysis, personalized monitoring and screening, transfer learning, and AutoML. This type of analytics cannot be incorporated in clinical practice unless they represent interpretable methods that the clinicians and patients can understand and take into their decision-making, as well as provide uncertainty estimates and confidence estimates associated with these predictions, such that the clinicians will know when they should trust the predictions that are made and for what patients and when they cannot. Last but not least, we are actually building, as we speak, a new area of research in machine learning that we call quantitative epistemology. And the focus here is understanding how humans learn and make decisions. The focus behind this is to build a quantitative approach to enable man and machine to interact more effectively. So the focus is not replacement of clinicians and medical researchers, but rather empowering them. And for that, man and machine need to understand each other. So we are doing a lot of work at the interface of inverse reinforcement learning, inverse decision-making, and going one step further. I'll not talk about this topic today, but I hope that I'm going to come to RISE in not too long post-COVID, and I will be able to tell you more about this research topic when I'm coming. If you want to see why machine learning is such an interesting area and why it requires the development of so many machine learning methods, you can take a look at our recent NeoRIPS publications, and you are going to see that the area of healthcare really demands new methods in machine learning in a variety of areas. Today, I'm going to talk about 3 main areas. I'm going to briefly talk about automated machine learning. Then I'm going to talk at length about individualized treatment effect inference. And I'm going to finish this talk by describing methods for machine learning interpretability. So a first problem that I'd like to highlight is the fact that patients are complex, and they often have not one risk, but rather multiple risks. This is especially true for elderly patients, which may suffer from a variety of morbidities and comorbidities. Yet currently, when patients are visiting clinicians, they are assessed for risk for a particular incident or a particular disease, and this is often done independently. So what we are trying to do here is develop a holistic view of the patient that looks at multiple scores and makes predictions over time for multiple clinical conditions and looks at these conditions and the way in which these conditions evolve over time in an interdependent way. So how machine learning can help with this type of personalized medicine that we often call bespoke medicine, because it's not only looking like in personalized medicine and precision medicine, just at clinical variables and genetic variables at onset, but rather is looking at how patients evolve and evolve over time. So machine learning can contribute a lot to this agenda, both because we need to evaluate the health of a particular individual and the probability of developing a particular disease over time. But also, we don't want to do that only based on current information. We would like to develop methods that are potentially considering the clinical knowledge and the medical knowledge evolution over time. For instance, this is best exemplified with COVID-19, where early in the pandemic, we knew relatively little about the condition of the patients, and maybe the variables that were collected about the patients with COVID-19 were relatively limited. But as our understanding has progressed, we are collecting more variables that are important and informative to know how to treat patients more effectively. In order to do so, we could use machine learning methods in a brute force way. But this is both prohibitively expensive and also to build a variety of risk scores at the push of a button would require quite a lot of expertise. So instead, what we are proposing here is to do automated machine learning, where machine learning itself can do the crafting of such clinical scores. So automated machine learning can select the machine learning model to use for a new data set, as well as tune the hyperparameters of the models chosen, and possibly integrate the different models that are selected. In medicine, we need to go one step further because there is quite a lot of missing data, inclusively data that may not be missing at random, informatively missing data. So missing data is another component that needs to be considered when building machine learning models for medicine. Also, acquiring a wealth of information may be costly, both for the patient as well as the healthcare system. So doing active sensing and evaluating what information we should acquire for which patient and when represents part of the research agenda. Also, how shall we really evaluate the performance of a particular machine learning model in the clinical setting is important, and this may be problem specific, and we may need to consider the fact that the data may be biased as well as imbalanced. Last but not least, we would like to have uncertainty estimates associated with the predictions we are making. So what we would like to do is we would like to issue a variety of risk scores at scale on the basis of the clinical data that we have. And the reason this is challenging is that the design space of possible solutions is vast. We need methods for data imputation, for feature processing, feature selection, prediction, etc. We have first addressed this challenge in a paper a few years back that we call autoprognosis. And the focus here was to build a tool for crafting clinical scores at scale using machine learning. So we take a clinical data and a particular outcome of interest, and we issue predictions using pipelines. These pipelines contain data imputation methods, feature processing, prediction as well as calibration. And depending on what algorithm is chosen at a particular stage of the pipeline, the algorithms that precede it in the previous stages or follow it in the next stage may change. We not only issue predictions on the basis of one selected pipeline, but rather integrate multiple pipelines through an ensemble construction. And in this way, we issue predictions. We also issue explanations associated with these predictions, and I'm going to talk more about that later. But what I'd like to highlight here is that we don't only learn on the basis of the data collected at one particular hospital or even one particular country. In many settings, we would like to learn from other complementary cohorts. An example, again, in there of COVID-19, where early in the pandemic, there were very few countries that had a lot of cases. Yet we wanted to learn from other complementary cohorts from other countries. But these other countries may have different characteristics in terms of the population that was affected, both in terms of comorbidities, genetic information, etc. So an important point when issuing such predictions is not only to learn from the current local cohorts, but also other complementary cohorts, even though these cohorts may have different characteristics and may suffer from different, may have different distributional shifts and feature mismatch. I'm not going in view of time to talk today about autoprognosis at length. You can find more about this on our website. But I'm going to just say that this is a wonderful tool that can be applied for a variety of predictions. And we have used it ourselves to issue predictions in cardiovascular disease, cystic fibrosis, breast cancer, and more recently, COVID-19, as well as breast cancer therapeutics. In the area of COVID-19, this is especially an important agenda. So because our lab is working on machine learning for healthcare, early on in this pandemic, we have identified a variety of different areas where machine learning can help respond better to COVID-19. I just highlighted in the previous page a paper that we have written early on in the pandemic in March 2020. And then we have identified 5 different areas where machine learning can help better respond to COVID-19. Manage limited resources, develop personalized and effective treatment courses for each patient, inform policies and improving collaboration to better respond to COVID-19, inclusively looking at better methods for making sure that lockdown is implemented timely and effectively, as well as released timely and effectively, clinical trials in there of COVID-19, and more generally managing uncertainty. You can read more about this research agenda on the previous slide, but for the sake of seeing how we implemented this agenda in these 5 different areas, you can take a look at our website where we show the different projects that we have undergone in the last year to address this research agenda and work with a variety of partners to really hopefully make a difference. One particular project that I just briefly want to highlight is our partnership with NHS Digital in the UK, where we have used autoprognosis to help hospitals plan and manage better COVID-19 treatment resources. And together with NHS Digital, we have built a demonstrator and a system that has been tried in a variety of locations in UK, where we are looking at the resources, the precious resources that were needed at different moments in the pandemic at different hospitals in terms of beds and ventilators. There are many challenges associated with implementing machine learning at scale at the level of an entire country. And we are highlighting both the opportunities as well as the challenges that we have faced doing so in this particular paper. So you can take a look and see not only the methods which have been developed by us for quite a long time, but also what were the challenging points in implementing this effectively in a real system. Today, I'm not going to go in more details into autoprognosis, but I'm going to say that the automated machine learning agenda for medicine needs to incorporate other areas, not only prediction, but also time to event analysis, competing risk, causal models, and temporal models. And over the last few years, we have built in the automated machine learning framework more models for these particular classes of problems. Today, I'm going only to focus on the causal models, and I'm going to go into more detail in this. So the focus we are trying to of this problem is to issue personalized treatment recommendations for the patient in front of the clinician. So the focus will be to estimate the effect of a treatment or of an intervention on a specific individual given their unique characteristics. And this is important because treatment effects are often heterogeneous. They depend on the patient's characteristics. We know that often current treatment decisions are based on average effects of a treatment as observed from a randomized controlled trial. But unfortunately, these treatments are often resulting in a different population. So the focus is to estimate individualized treatment effects, and we are going to cast this as a causal effect inference problem. Again, I'd like to here the world of randomized controlled trials, which focuses on average treatment effects, that often includes as an inclusion criteria for this randomized controlled trials, non-representative patients. So patients that may be elderly or may have many comorbidities may often not be enrolled in a clinical trial. This has been the case, for instance, for COVID-19, where many of the trials that went on didn't include initially too many elderly patients or patients that have a lot of comorbidities. Also, they are often focused on a very specific question, and they are at times unable to capture the complexity of delivering healthcare. Also, the number of patients enrolled in a trial may be relatively limited, and this may be time-consuming and lead to enormous cost. So often a clinical trial is only going to focus on estimating average effects of a treatment. But again, we would like to focus on what will be the effect of a particular treatment on the individual. We would like a patient-centric approach. And for that, we would like to estimate treatment effects for the individual on the basis of real-world observational data. In this way, we are going to be able to capture the complexity of healthcare. We are able to have scalable and adaptive implementations that will be fast in deployment and cost-effective. I'm not arguing here to replace clinical trials, but rather to complement them. So in the era of randomized controlled trials, machine learning can add a lot. Current clinical trials are still based on very conventional methods, and it is my belief that machine learning can add a lot to this agenda, especially in the context of adaptive clinical trials. And our lab is doing quite a lot of work on this agenda, but I'm not going to highlight it today. I'm just going to mention it as an important, interesting area for machine learning. Today, I'm going to focus on estimating individualized treatment effects from observational data. So the focus here would be looking at the unique characteristics of a patient and estimating on the basis of observational data as extracted, for instance, from an electronic health record or a registry, what will be the effect of a particular intervention on the individual? Should we recommend to them chemotherapy or not? Shall we determine a particular dosage if we recommend chemotherapy? And what will be the best dosage for this particular individual? Then to highlight a few of the methods that we have developed, but if you want to read more about our work in this area and the research agenda, please take a look at our website dedicated to this topic, since this represents an important research pillar of our work. So today I'm going to introduce the formalism and present a few ideas. So unlike in the setting of autoprognosis, where the focus is to predict whether a patient is going to, for instance, die or have developed cancer during their lifetime, the focus in this setting is to estimate the effect of a particular intervention or treatment on an individual. So our data set will contain the following information: patient's characteristics, XI, and a decision on whether to treat or not to treat a particular patient. For the sake of simplicity here, I'm going to look only at binary treatment effects. So I'm going to assume that the patient is either treated or untreated. But the reality is that the methods that I'm going to describe are going to be, we can extend them to more than one treatment. And what we observe, given the particular decision made, is the outcome of that particular intervention. We do not observe counterfactuals. However, what we would like to estimate is the effect of different types of treatments on the specific individual. So we are actually trying to solve a causal effect inference problem rather than a supervised machine learning problem. And the reason this is challenging is the fact that we do not have explicit labels. We observe the factuals, but not the counterfactuals. Yet we are trying to estimate the treatment effect and the difference between the different possible interventions. Another challenge associated with this causal effect inference, besides the fact that we do not observe counterfactuals, is the fact that the data is biased by the clinical practice. I'm not going to talk much about that, but this is a problem that needs to be solved in this setting. The I'd like to describe first is the fact that this research agenda has been ongoing for quite a large number of years by now. And many different types of methods have been developed to solve this particular problem, both in statistics, econometrics, and machine learning. What you see here is a few papers that have been developed up to 2019 from a variety of research labs, inclusively our own lab. So the papers that have, the methods that have an arrow in front of them were developed by our own lab. And this is just a small subset of papers. The challenge is, though, if we want to automate causal effect inference, unlike in the case of autoprognosis, where we can observe the labels, we cannot do simple cross-validation. And the reason behind it is because in this case, we do not observe the counterfactuals. We do not have labels. So the question that we tried to solve in this ICML 2019 paper was, how can we do AutoML to select the best model for each observational study, given the fact that we need to really do cross-validation, and this is not possible given the fact that we don't have the counterfactuals. So in order to understand this problem better, let me mention that the way in which currently we estimate the effect, the causal effect inference on an observational data set is by introducing a mean square error of a causal model. And this is denominated as PEHE, which stands for precision in estimating heterogeneous effects. And again, the challenge here is that we observe only the factuals. We do not observe the counterfactuals. So the issue we need to solve is we need to find a way to validate causal models without observing the causal effects. For that, we are building on a relatively simple insight. And this simple insight comes from Taylor series approximation. We know that from high school that if we want to estimate the value of a function at a given input, we can do so by predicting its value at a proximal point. So for instance, we want to estimate the value of a function at x1 given the observations we make at x0. And we can do so by approximated fx1 using a Taylor series approximation. In an analogy with the Taylor series approximation, we can estimate the performance of a causal inference model by realizing that we now no longer deal with functions, but functionals, so function of a function, of a data generating distribution. So in this way, we are able to use the synthetic distribution with known counterfactuals to estimate the causal inference model. Instead of a Taylor expansion, we are going to use, because we now have functionals, we are going to use von Mises expansion, so functional calculus, and we are going to substitute derivatives with influence functions. And what you see here is the distributional analog of a Taylor expansion using influence functions. And what we can do in this way is we can predict the performance of a causal inference model using the influence functions of its loss on a similar synthetic data set. So we are going to be able to estimate in this way, based on the factuals, the effect of the causal inference model. So what we are doing in a two-step way is synthesize counterfactuals. First, as a first step, we are doing plugin estimation. And then, because we are dealing with biased observational data, we are going to do bias correction. So we are going in this way to synthesize counterfactuals. And we are going to estimate using this first order Taylor approximation the true distribution, which is an inaccessible empirical measure for the case of causal effect inference. But we are going to estimate this true distribution by making use of accessible empirical measures for the synthetic distribution and approximate this true distribution using von Mises calculus using influence functions. Now, with this tool in mind, at our disposal, we have implemented the validation step using influence functions. And what you see here is the performance of this automated machine learning method based on influence functions and its performance as opposed to any individual causal effect inference model. So what we have done is we have used the Atlantic competition, which has 77 benchmark data sets for causal effect inference. And what you see here is that any model alone was not better than 17% maximum of the time. You see here in pink some of our own methods, and you see that their performance is quite good, but compared to the overall performance, they are only a winner in only a relatively small percentage of the data sets. What this automated machine learning framework based on influence functions does, it selects the best model out of the many available models for the causal inference data set, and it selects the winner 72% of the time. So now, equipped with this, we can do automated ML for the sake of causal effect inference as well. Again, more about the different methods that were used, as well as the AutoML framework on our website. Now, let's say that we like to do that not only based on static variables, but we would like to do that in an integrated way over time. So we would like to use temporal, longitudinal data. We would like to do that for both prediction as well as treatment planning, as well as monitoring. So we move from a static cross-sectional data to a time series data. And in a recent research work that we call clairvoyance, we have built a unified end-to-end pipeline for clinical decision support system. And we believe that this is an important milestone in machine learning research, because prior to this, everyone trying to do research in time series clinical data was using a different set of benchmarks and a different set of methodologies. So in order to enable reproducibility, we created this framework, clairvoyance, where methods can be easily added, plugged in, and compared against other state-of-the-art methods. And similar to autoprognosis, but now for time series setting, we are doing data imputation, prediction, treatment effects, and monitoring. I'm going to briefly highlight what 3 particular components of clairvoyance. And I'm going to start by looking at treatment effects, but now treatment effects over time. So unlike in the previous setting where we were having variables only at onset, now we are going to have longitudinal variables acquired over time. And what we are going to try to estimate is the effect of interventions at different moments in time and try to estimate the best treatment plan for this particular individual given the past history so far. We are going to try to estimate how to treat a patient, but also with what type of treatment, as well as when to give treatment and when to stop treatment. To be able to decide the best treatment plan, we need to estimate treatment effects for the individual on the basis of biased observational data. So what we have at our disposal is time-dependent patient features, X, time-dependent treatments, as well as static patient variables. This represents the patient history. And what we would like to estimate is what will be the best treatment plan for this individual given the history. And we will try to do that on the basis of the available data. Casting this problem in the Neyman-Rubin framework, but because we look in the longitudinal setting, the work of Robbins and Hernan is very pertinent here. So we are going to look at potential outcomes under planned sequence of future treatments. So we consider the history and we are estimating the outcomes given this history. We are going to make 2 assumptions in this framework, which are usually made in this setting, and they are quite strong, but important for this framework. One is that of sequential overlap, and the other one is that the fact that we don't have hidden confounders. So we are going to have sequential strong ignorability. The focus here will be on estimating, given this patient history, which contains time-dependent confounders, which are biasing the treatment assignment in the observational data. So we are going to make this estimation of the best treatment plan given these time-dependent confounders. And these time-dependent confounders are patient covariates that are affected by past treatment, which then influence future treatments and outcomes. And you are going to see in this example highlighted here, the bias we are going to have from the various time-dependent confounders. So this is highlighted here through this graphical model. And we will need to learn what is the best effect, the best treatment plan for this patient, given these time-dependent confounders. One particular way to address this issue and handle time-dependent confounding bias is by doing inverse probability of treatment weighting. And this is what marginal structural models introduced by Robbins and Hernan have done already for 20 years. In recent work built on top of these models, we have built on top of these marginal structural models, and we have introduced deep learning models to learn the dependencies over time. And the point here is that we cannot just apply, as I mentioned before, supervised learning to estimate such potential outcomes. And this is again due to the bias from the time-dependent confounders. So we will need to really address this problem. The challenge, though, in using such inverse probability of treatment weighting is that we need to create a pseudo population where the treatment probability no longer depends on the patient covariates. And in this chosen population, the counterfactual estimates are unbiased. However, these inverse propensity scores results often in high variance estimates due to extreme weights, and often may be numerically unstable when the treatment population is very small. So to solve and address this challenge, we went one step further and we built a new representation learning approach to deal with this issue. And that is our work on counterfactual recurrent networks. So what we have done here is we are building treatment invariant representations using domain adversarial training, and we estimate counterfactual trajectories using a sequence-to-sequence architecture. And in the sequence-to-sequence architecture highlighted here at the bottom of the screen, the encoder uses domain adversarial training to build at each time a representation of the patient history that is treatment invariant. And this, in this way, breaks the association between the patient history and the treatment assignment, thus removing bias from the time-dependent confounders. And then this representation is passed to the decoder, which is continually updated while estimating the outcomes. As I mentioned, we are training these representations using adversarially balanced representations. And for that, we are actually building on the framework of Ganin, which proposed an adversarial framework for domain adaptation, which involves building representations which achieve maximum error on a domain classifier and minimal error on an outcome predictor. But we are using in this setting domain adversarial training to build representations of the patient history that is both invariant to the treatment given at a particular moment in time, and that achieves low error in predicting the outcome. We have used this type of model and validated in a variety of settings. One particular setting that we used is a synthetic model that is built on a variety of pharmacokinetic models. And the reason we use such a semi-synthetic model is because it enables us to play with the different parameters and see the performance of the model under different amount of different types of time-dependent confounding. And what we are showing is that as opposed to marginal structural models and recurrent marginal structural models, we are able to improve significantly both in terms of treatment accuracy as well as treatment timing accuracy. Now, you can play with this in our clairvoyance and compare the different models and a variety of other models developed by us and others within clairvoyance. Briefly, I'd like to highlight one more component of clairvoyance, especially since this is quite close to an important area in electrical engineering, and that is of sensing and active sensing. Active sensing is very important in medicine because this leads to methods for personalized screening and monitoring. So if you are interested in identifying for a particular patient when to screen, and what type of information we would like to acquire, and possibly with what type of modality. This represents a well-known area in engineering of sensing and active sensing, but this corresponds in medicine to the idea of personalized screening and monitoring. The challenge here is that we will need to estimate the value of information and the value of information over time based on observational data. So we cannot do experiments on patients and see what would happen if we screen them more or less or with different types of screening. We will need to learn and estimate the value of information from observational data. So unlike in the existing literature in active sensing in communication systems, for instance, which is a well-developed, mature area, in medicine, we need to deal with the challenge of estimating this from observational data, which represents unique challenges. We have made some progress in this area, and you can see this in these few papers highlighted here, but a lot more can be done. And this is an area where I think the engineering community can contribute a lot in medicine. Let me now go to the final part of this talk and talk briefly about interpretations and interpretability. So in order to make machine learning suitable for clinicians and actionable for them, we need to have interpretabilities. of different sorts. We need to have machine learning interpretability. We need to have trustworthiness associated with the model predictions. So we need to issue not only predictions, but also confidence estimates associated with these predictions. But we also may need to provide explainability. And what I mean by explainability is different types of explanations for different types of users. Because a clinician may want a different type of explanation than a patient or a medical researcher. I'm going to highlight this a little bit more a little bit later. Let me start by discussing what interpretability may mean. One particular way of thinking about interpretability is highlighting what features were important for a particular prediction. So we may have a prediction, for instance, using autoprognosis, which is a black box model for mortality from COVID-19. And the prediction accuracy may be quite high. But the clinician may wonder why the model has issued this high probability of Mary dying from COVID-19. So we can inspect this particular black box model and we can identify that, for instance, autoprognosis has looked at age and hypertension when issuing this prediction for Mary. We can identify the unique individual features that were relevant for the black box model when issuing this prediction. So what we are doing in this setting is we have built a model that we call InVade, which is identifying what features is the black box model looking at when issuing a prediction. This method can be put on top of any black box model, static or dynamic model, and identify variable importance and variable importance over time for the individual. How are we doing that? We are doing that using reinforcement learning. So the different observations, which are in this case the features of the patients, are the input. And then the actions are what observations are the machine learning model thinks are relevant for this prediction. And the rewards are the predictive performance given the selected features. We can train this in a variety of ways, but we have opted here to train it in the simplest possible way using an actor-critic framework. So in this way, InVade is learning how to build policies that are estimating the feature importance for a particular prediction. Let me highlight this with a particular example here. So we have a black box model, and this may be a neural network or autoprognosis. And we want to learn what features is the black box model looking at when issuing a prediction for an individual. For that, we are going to determine through an actor, which is a selector network, which takes as input the instances and outputs a vector of selection probabilities, which are the features selected for this particular individual, which the InVade framework believes the black box model is looking at when issuing a prediction. So the actor selects as an action the selected features for the black box model, which are then passed to the predictor network, which is issuing a prediction solely on the basis of these selected features. The error in prediction, in predictive performance between the predictor network looking at only the selected features versus the network looking at all the features, this error is the error formed by the critic, which is informing the actor to better select probabilities in the future for what features are important. So in this way, using a simple reinforcement learning framework, we learn what features are important. InVade is an individualized feature selection and feature importance method. It can be used in a post hoc way to identify which features are important for any black box model, and is in this way similar to learning to explain, sharp, or line. But unlike some of these other methods, it goes one step further because the number of features that are relevant for every instance does not need to be specified in advance. Is learned and is determined for every instance. So maybe for Mary, there are two features that are important and the black box model is looking at when issuing predictions. But maybe for Bob, another patient, another instance, a different number of features and different features are important. So unlike Lime learning to explain or Schaar, where this number of relevant features needs to be pre-specified, Invase is learning that. But is this enough? We learned when using such interpretable methodologies for machine learning that while this type of interpretation may be sufficient for other settings, this is not enough for the clinical setting. We need much more than that for methods to be adopted in clinical practice. In many settings, we need transparent risk equations associated with a black box model if it is for this model to be approved for clinical practice usage. And also we may need to go beyond interpretability and offer a variety of explanations. So just identifying features and feature importance is not enough. So we worked on this for a few years, and we wonder for some time whether it would be possible to provide all this. And in a research work 2 years ago, we have a method that is able to provide all these different types of explanations. And we are doing that by demystifying black box models using symbolic metamodels. So what do we do here? We take any black box model and we build for it symbolic metamodels, which can be represented as transparent white box models. What is a metamodel? Is a model of a model, and a symbolic metamodel will take as input this black box model and will output transparent functions describing the predictions of this black box model. An advantage of this methodology is that we do not need to know what's in the black box model. The intellectual property of that particular model can be kept private, and we only need query access to the trained black box model. What we are going to do is we are going to take the black box model and project it into an interpretable metamodel space that is selected by the user. So the metamodel space is selected, for instance, by the clinician, and they may decide that only polynomial metamodels are effective, or only polynomial explanations maybe are acceptable for use in clinical practice. Other experts may be okay with other forms of metamodels. How are we going to achieve this type of projection from the black box models to the white box models? We are going to be able to do that by making use of a powerful theorem, the Kolmogorov-Arnold theorem, which simply says that every multivariate continuous function can be written as a composition of univariate continuous functions. And in this way, we can project metamodels and we can represent them by approximating them using interpretable basis functions. So we take a black box model F and we find in the interpretable model space that's selected by the user, interpretable basic functions J that are closest in this space to the black box function F. How are we going to learn that? I'm going to describe in a little bit. But before I do that, let me say that one particular type of basic functions that we can use are Meyer-G functions. And since in this particular audience, many of you in communication systems may be familiar with Meyer-G functions, let me just say that while in communications, Meyer-G functions are very useful, in this particular problem, they are useful because they can represent a very general class of functions which for different parameters are leading to desirable familiar functions that can be selected for interpretability, such as polynomials, exponential, Bessel functions, etc. how do we learn the parameters, the metamodel, to best approximate the black box model? We are going to do that in a similar analogous way that we learn hyperparameters for neural networks. We are going to be able to do that simply by doing gradient descent. So very simply, by learning the parameters of the metamodel and combining these Myers-G functions and learning the parameters associated with that. If we are able to do that well, we are able not only to issue predictions, but also interpretable predictions. So if it is to use COVID-19 example, autoprognosis is doing significantly better in predicting mortality from COVID-19 as opposed to an interpretable statistical model such as the Cox proportional hazard model. However, autoprognosis, while being more efficient in terms of predictive accuracy, it is also uninterpretable. So we can use symbolic metamodels to interpret these predictions and come up with white box explanations associated with it, symbolic metamodels associated with it, that are transparent equations. In this way, we are able to approximate the autoprognosis model, and at the expense of a very limited decrease in performance, we now can use these interpretable metamodels to issue predictions. So the autoprognosis framework has led us to finding the metamodel, but now that we have found this metamodel, we no longer need it. We can use the metamodel itself, the symbolic metamodel, to issue the predictions. So we have an interpretable equation, nonlinear equation, but an interpretable one that is significantly better in performance than the Cox model. So you see here an example of how such a metamodel may look like, and you can see that in some settings, it may be a complex nonlinear equation. However, because it's an equation, we can easily investigate it. The clinicians and patients can easily look at this metamodel and understand what is, for instance, individual level feature importance. And unlike in models such as InVase, Learning to Explain, or Schaar, or Lime, where we can only locally look at variable importance and only look at variables that are important, but not how they eventually depend on other variables and how exactly they will change as we are perturbing one variable. So sensitivity analysis is not possible. Using metamodels, this is easily possible since we have analytical formulas associated with it. Using that, we can then provide a variety of explanations for researchers and patients and clinicians. For instance, using the symbolic metamodels in the forward use, we can look at the effect of features on risk, variable importance, variable interaction, as well as hypothesis induction. As well as in the backwards use, we can see how can we reduce risk for a particular patient. Are there any variables that we can act upon, either using a drug or a particular intervention, in order to reduce the risk of this patient from dying from this particular disease? If you want to hear more about a conversation that I have had with clinicians about interpretability in healthcare, you can take a look at this talk, which I have given at the Turing Institute at the beginning of this COVID-19 pandemic. And you can see more about the different methods we have developed, as well as what clinicians find interesting when looking at machine learning models, what they would like to see to make these methods actionable in clinical practice. That being said, I arrived at the end of this talk, and I highlighted to you a few research topics that we have worked on over the last couple of years, and especially developing actionable intelligence on the basis of electronic health record data to inform clinicians to improve clinical practice, as well as enable data-induced hypotheses, as well as using a variety of other data in addition to electronic health records, especially omics data, to augment current clinical records and provide genetic information in addition to electronic health record data, and learn from a variety of information. Also, we are working closely with pharmaceutical industry to understand better what treatments are most effective for what patient and when. We know that currently a lot of these treatments may be effective for some subpopulations, but not others. So identifying what treatments are most effective for what patient is an important agenda that we are working on. Finally, if you are interested in this topic, I hope that you maybe can join us in a community that we are building. So we have started, because of the pandemic, an online engagement session with machine learning students and researchers from all over the world that are interested in developing methods for healthcare. If you are interested in this, please go to our website and subscribe to this engagement session and talk to us about building together a community to empower clinicians with better methods. Thank you.
Thank you very much. Wonderful talk. So I'd like to open the floor for questions. Then I can see there's a question from Soptic. Do you want to speak up, Soptic?
Yeah, sure. Hi, Dr. Vandashar. I think, like Akane said, great talk. And my question was on slide 32 for the AutoML results that you shared. And I believe maybe you answered that question later. So my question was, you said that I think it was the AutoML model, which was the best model across many models in a causal in over 77 benchmark data sets and in the causal inference task. I just was trying to get a sense for one specific task, if you could share, like what was the task, what was the input, and what were you trying to estimate, and how do you assess a causal inference model in that case? And how would you estimate how good your model is doing?
So thank you for this question, which is a very good one and somewhat challenging. So in this causal inference competitions, or whenever somebody is benchmarking a model in this setting, what we often have is semi-synthetic data. So we do not know in practice, in clinical practice, counterfactuals. There is no way we can go back in time and say what would have happened if you would have done something else. So usually what people do in this literature, in the machine learning community, as well as statistic community, we take clinical trial data where on the basis of which we can generate the counterfactuals, and then we introduce different types of biases. So in this competition, in the Atlantic competition, we do know in these semi-synthetic data sets the effect of the counterfactual. This is why we can estimate the true error, the true mean square error, because we have both the outcomes available in the data set. So the way in which we are estimating that is using this semi-synthetic data set. So this is why we can estimate it in the end. But when we are training these models and we are employing this AutoML framework, we do not have access at training time on these counterfactuals. So at training time, we only observe the factuals. We are estimating the best models using this influence function methodology and estimate the best method for this particular new data set and select the best model that we believe using these influence functions would be the best model for this data set. And then we are validating that on the semi-synthetic data set to see indeed what was the true performance. That being said, this is of course something you can do in a competition. You can do using these semi-synthetic data sets to estimate the effect of these counterfactuals. But in reality, you often may not have such a situation. You may have only observational data without counterfactuals. In that setting, often you would validate this using just observational data. So you will estimate only the error on the observed variables, but since you never will know in reality the counterfactuals, you cannot do that. Do I make sense? It's a little
Yes, yes. Thank you so much. That was great. Yeah, thank you.
Thank you. So often for this causal effect inference, I would say one of the research agendas is how can we build better, more realistic semi-synthetic models to validate well such causal effect inference methods. And one way is to use pharmacokinetic models, which I have shown in the second part of the talk. Another way is using clinical trials and then create post hoc observational data and bias it ourselves.
Okay, thank you so much.
Thank you.
I saw Benham raise his hand.
Hi, great
Hi.
talk. Really enjoyed it. We got to meet in 30 minutes or so. I have a question. I was wondering how prevalent is the Gaussian assumption on the data in your community, and are people now moving away from that and sort of getting more data driven, or are they still sticking to Gaussian models?
Thank you so much for that. No, in this community, people have realized that definitely the population is not Gaussian. So increasingly, models that have new types of generative models, non-Gaussian models have made a very big, I would say, entry. So I would say data-driven models are very important. However, at times, putting priors that are Gaussian may still happen. So you will see still some literature where people start with some priors that may be Gaussian and then learn in a data-driven way on top of it. Some other people and some other strand of literature doesn't even make that assumption and learns a variety of generative models, removing this assumption kind of completely.
Thank you. Thank you.
Thank you.
Then let's move on to Alicia.
Hi, thank you for the presentation. I have a question about the semi-synthetic data sets. I don't know how much synthetic data you're using and how do you generate the synthetic data, and also how you use it along with the real data set.
Thank you. So here are, let me say that I use the word synthetic to mean two different things, and that may be somewhat confusing. So in the very beginning of the talk, I said that we are working a lot on synthetic data generation. I will clarify what that means in a little bit. But in the second part of the talk, I use the word synthetic data and semi-synthetic data to refer to the fact that in this causal effect inference problems, we do not observe counterfactuals. So because of that, we often use, for instance, pharmacokinetic models to generate this semi-synthetic data such that we have access to counterfactuals. But in the beginning part, so I was the word synthetic and semi-synthetic in that context. But in the beginning of the talk, I talked about synthetic data in a different setting. So often when I give a talk like that, people will ask me, well, you may have had access to some very special data. For instance, in the work on COVID-19, we were very fortunate to work together with NHS Digital in the UK and have access to some very unique data sets. Yet we can't share these data sets with the broader machine learning community. And this is a big problem because if you want to have reproducibility, if you want to select the best models, we would like the entire machine learning community to work on the same data sets and empower the entire community to build models and share results. And this is not possible when we cannot share data. So because of that, we have worked quite a lot in the last couple of years to build generative models for synthetic data with privacy guarantees. We work, for instance, on a variety of generative models based on GANs, inclusively time series GANs, generative adversarial networks, as well as some other models based on normalizing flows. So we are building synthetic data that is generated on the basis of the real clinical data, but because the clinical data cannot be shared with the researchers, we generate synthetic data as trained on the basis of the real data and just release to the research community the generative models. The challenge with that is that we need to release them in a way in which they are of high fidelity, such as the researchers that are training models on the basis of this synthetic data have the confidence that the analytics they build, the machine learning models they build, are truly useful when taken to the real clinical data. And conversely, the owners of this data, the clinical community, has the guarantee that the privacy and anonymity of these data sets is not violated. So, for instance, differential privacy may play an important role here. And we have run actually at NeurIPS 2020 a competition that we call the hide and seek competition. And the focus of this competition was to generate synthetic data with high fidelity and high privacy. So I also mentioned the synthetic data in that context. Does that make sense? So two different uses of synthetic data in this talk. Sorry for a little bit confusion maybe on this.
Yes, thank you.
Okay, so I'd like to thank again Professor van der Schaar for wonderful talk and the interesting discussions. And a few of us will be seeing you after this talk, so we are looking forward to it.
Thank you so much. Thank you.
So I'd like to conclude today's seminar. So thanks again, Professor van der Schaar, and also everyone for joining today's wonderful talk. Thank you very much.
Thank you.